So hello everybody. In this video we're going to talk about fields. A field is a mathematical structure that comes in help when we want to extend the notion of numbers, right? We are used to work with real numbers, rational numbers, and maybe sometimes complex numbers. These are examples of fields. I'm sure you've already worked with R, the field of the real numbers. Also, when you were in high school, I'm sure you talked a little bit about fractions, so you know what the rational numbers are. And some of you maybe experienced some work with complex numbers, maybe when you were in college or maybe even in high school. So we're going to discuss the notion of field in a more general fashion, and we're going to explain how fields work and help us, especially when we want to define polynomials over a field. So more or less what we want to say is that a field is a set of numbers or a system of numbers. Maybe number is a more familiar term for all of you, but we want to emphasize that we are extending the notion of number to a field, right? So elements of a field are what we used to know as numbers. So what is a field anyway? We need to define what a field is, right? So here comes the first definition. A field is a set F together with two operations called addition, that we're going to note with a plus sign, and multiplication. Noted with a dot, right? Such that. So a field must satisfy a certain group of conditions, of axioms, in order to work. So first of all, the operation plus takes two elements of the field and produces a new one, right? So this is what we call a binary operation that takes the pair AB and produces a new element called A plus B. See, this is the new number A plus B. This operation plus or addition has to be commutative. This means that A plus B has to be the same as B plus A. Then it needs to be associative. So A plus B plus C equals A plus B plus C. So we're going to write this down, right? So this means that A plus B has to be the same as B plus A for every A, B, and F. Then association means that A plus B plus C has to be the same as A plus B plus C, right? Another thing we're going to ask for this operation is that there exists element 0 sub f such that 0 sub f plus a is the same as a plus 0 sub f, and this is a for every a in f, right? Obviously, this element has to play the role as a neutral element for addition, right? So that is 0 sub f is like the zero number. It's like the zero element. And also for each element of the field, let's write it like this. For each a belonging to f, there's an element a prime also in f such that a plus a prime equals a prime plus a, and this is 0 sub f. A prime is known as the additive inverse for a. Right, so this is like the first set of things that we need the operation plus to satisfy in order to have a field. Obviously, this operation that it's noted with a plus sign is actually mimicking all what the ordinary addition of numbers does. So we are relying on the same symbol just to fix ourselves to the idea that adding elements of a field is just like adding numbers, even if they are not numbers, okay? It's like a reminder that this operation works just as we know addition works, right? So these four axioms define addition on F. We will have another video going deeper into this sort of binary operation. If we just consider F and this operation, what we have is an abelian group. That structure is a very interesting one, appears in all of mathematics, and we're not going to spend more time than just a definition here, but it's a very fruitful structure. And so we were saying that we have addition and we also have multiplication. We're going to speak some things about multiplication now. So 2. The multiplication operation. So it's denoted with a dot, and it's also a binary operation. That means we take two elements of F and we construct a different element for F. So if we take the pair AB, we produce the pair A times B. So we are going to ask this operation to have certain properties, and pretty much in the same fashion that we did with the addition, right? So we have number 5, dot is commutative, and 6, dot is associative. That means that A times B is the same as B times A for every A, B, and F. And this means that A times B times C has to be the same as A times B times C. It's also for all A, B, C, C in F, right? So this operation has to be commutative and associative, right? Then we're going to ask for the existence of a very special element for the field that has the following property. There's an element E belonging to F such that E times A equals A times E equals A. So this element E works as a neutral element for multiplication. So we say that E is the neutral element for multiplication, right? It works just as if it were a 1, okay? And we have to ask, and E has to be different from the 0 element. So this prevents the trivial cases for rings. We're going to work with rings where the neutral elements for plus and multiplication are different. This sounds like a very technical assumption, and it is. It is a technical assumption, but saves us a couple of headaches in the future. This is what we would ask for anyway. So there's an element that works as 1, and we're going to ask for some more things. What do we have now? We can distribute addition and multiplication, right? So we're going to say A times B plus C has to be the same as A times B plus A times C. So we can distribute multiplication in terms of addition. So there's a final condition that we're going to impose on this multiplication operation that's going to ensure us that we have all the properties that we need. Number 9, each A in F that is not 0 has a multiplicative inverse. That is, there exists an A hat such that A times A hat is the same as A hat times A, and this is E, the multiplicative neutral element. So what this means is that each number that is non-zero can be inverted in that field. Usually, the inverse is noted A to the power of -1, also 1 over A. So this is notation for the multiplicative inverse. So all these conditions or axioms are what define a field. So a field is a set bundled with 2 operations called addition and multiplication, subject to all these 9 conditions. Okay. Once we set the definition, we're going to show some examples and some non-examples as well. So let's do that now. examples and non-examples. So let's start with a non-example. A set of natural numbers. Set of natural numbers is the set 1, 2, 3, 4, and so on. Where these are the numbers that we use to count. Right? We learn about these numbers in kindergarten. So what is it? Why is it that n, the natural numbers, is not a field? Well, for a number of reasons, but we can say that n is not a field because there are elements in n that have no additive inverse. Well, as a matter of fact, none of them have additive inverse. Yeah, 2 has no inverse respect to addition in n. You know, that is, we can say that like there is no solution to the equation 2 plus x equal 0. N. Right, there's not even a 0 in n. So n is not a field because it has no 0 element respect to addition, no additive inverses respect to addition. So n is not a field. Say that we are now interested in looking at z, like the whole numbers. Also known as integers. Well, z consists of all the natural numbers added with 0 and the negative numbers. So it's 3 minus 2 minus 1, 0, and then all the naturals. Right. So now we have fixed this thing of not having the inverses, because now each number has an additive inverse. Say 3 plus minus 3 is actually 0, and this happens for every number here. And for each element of z, there's an additive inverse. But what lacks is multiplicative inverses. That is the equation 2 times x equals 1 has no solution. Inside. So the natural numbers are not a field. They do not form a field because we don't have an additive neutral element. Z has all the inverses, has a neutral element which is 0, but has no multiplicative inverses. So cannot be a field. Well, there's a field that we can form, and we know this field for a long time. It's Q, the field of rational numbers. Right? And this accounts for the set of fractions, right? So it's composed of symbols noted A over B, such that A is in Z and B is a natural number, right? So rational numbers do have inverses for both addition and multiplication, and they work just fine for most purposes, right? And also, we have a bigger field that contains Q, if you will. It's the set of real numbers. Real numbers. So the real numbers include the rational numbers as special cases, and also limits of sequences of rational numbers. If you don't know what a sequence is, just don't worry, we're going to cover that in a separate video. But what we want to show here is that we have this sort of chain of containments. Right? We started with natural numbers, then adding the additive inverses and 0, we get the integers, and when we add the multiplicative inverses, we get Q. Okay? So adding now limits of sequences of rational numbers, we got R, set of real numbers. So here we have lots of things to work with, and also if you think a little bit more, this is contained in C, so complex numbers. Yeah, search as examples, but we're not going to concentrate on the nature of Q and C and R, and we're going to discuss the properties of fields themselves, right? We're going to go a little bit more structural on this topic. So next thing we are going to talk about are field morphisms. So let F and L be two fields. So definition: a field morphism F from F to L is a function such that it's compatible with addition. F of the addition is actually the addition of the images. Then F of multiplication is the multiplication of the images, right? And what we have is that we needed to send the 0 element of F to the 0 element of L, right? Also, the neutral element of F for multiplication has to go to the 0 element, the neutral element of multiplication for L. So this is what we are asking when we're talking about field morphisms. There are functions that transform elements of one field into elements of a different field. It's not difficult to show that whenever we have this sort of function, this is an injective function. That is, two different elements of f end up landing in two different elements of L, right? So there are no two distinct elements from the field F that correspond to a single element of L, right? This is important because field morphisms allow us to view F as a proper subset of L. Observation? Field morphisms are injective. If you don't remember what injective means, just don't worry, we're going to have a different video talking about functions. We're going to explain that in more detail. So, f of the field f, like the image of f, can be seen as a subset of the field L, right? So this is a very restrictive condition. Okay, this is a very, very restrictive condition for a function to be a field morphism. Well, there are some things that can be said about this sort of functions, and the good thing is that whenever we can work with a field morphism, we're going to have lots of operations that can be performed within L or within F. So this is some sort of mechanism to send operations that are done in F to L. And we're going to make this more explicit when we talk about this next topic, which is finite fields. Now, this is a very important topic. A finite field is a field which has finitely many elements, right? How do we work with finite fields? Can we show any finite field at all? Well, we're going to spend the rest of this video trying to construct a finite field. And once we define what it is and how it can be achieved to have a finite field, we're going to show that that is a very useful construction, right? So how do we come about finite fields? So let's start with Z. Z is not a field, right? Because it lacks multiplicative inverses. So a field that lacks multiplicative inverses is called a commutative ring. Is called a commutative ring. Addition is commutative, multiplication is also commutative. Everything distributes nicely, associates nicely, but some elements do not have multiplicative inverses. So that's what's been lacking. We lack that sort of property. What is a possible thing we can do with C? Well, let's fix an element in C. Say it's greater than 1, right? We can define a equivalence relation in C by setting the following rule. We'll say that B is related to A according to N if and only if B minus A is a multiple of N. This can also be stated as B minus A is divisible by N. So there exists K in C such that B minus A has form K times N. So this relation, under this definition, defines what we call a equivalence relation. And the equivalence class of an element X in Z, we shall note it like X bar, is the set of all things in Z such that A is related with X, right? And we're going to work not with Z, but the equivalence collection. Now we will form a set made up of equivalence classes. We will look at the collection of equivalence classes of this relation. And we're going to note it set over this relation. Since this is sometimes too cumbersome to write, we are going to use this notation, set sub n. Do we have numbers here? No, we have sets. Those sets are exactly the equivalence classes of numbers. Okay? And there's an advantage. Originally, observation set is an infinite set. It has infinite many elements. 1, 2, 3, 4, 5, etc., etc. It's an infinite set. When we look at the equivalence classes, we see that Z sub n is a finite set. Right? So the operation of looking at Z with this special sort of glasses that allow us to look at equivalence classes. We just see finitely many elements. So why? So if you take a look at 0, the equivalence class of 0 consists of 0, n, 2 times n, 3 times n, minus n, minus 2 times n, minus 3 times n, etc., etc. So if you take a look at the equivalence class of 1, you have 1, you have n plus 1, you have 2n plus 1, you have 3n plus 1, etc., etc. If you take a look at the equivalence class for 2, so we have 2, n plus 2, 2n plus 2, and so on. So the good thing is that if you start doing this with all the integers, the last one that you see that's different from the previous ones is the equivalence class for n plus 1, which is n minus 1. Then you have 2n minus 1, then you have 3n minus 1, and so on. So the collection of all classes is actually the collection of the equivalence classes from here to here. In other words, the collection of classes is the class of 0, class of 1, class of 2, all the way to class of n minus 1. If I wanted to look at the class of n, it will coincide with this one, right? So the set C's of n is a finite set, right? So with the help of the equivalence class, we were able to transform this infinite set into a finite one. But this is done in a very specific way, because this set admits addition and multiplication operations. This set admits addition and multiplication operations. So how do we do that? How do we define addition and multiplication? Well, it's not complicated. Say you want to add the class of A and the class of B. Okay, how should we do this? So we're going to define this as the class of A plus B. And how are we going to define the multiplication of equivalence classes? Well, we're going to define it as A times B, and then we take classes. So it should be noted that this addition right here is addition that is performed in sets of n. And this multiplication is also performed in this set. On the other hand, this addition and this multiplication, these operations, are performed in Z. So this addition and this multiplication are performed in a different place. So graphically what we have Z, which is our base set, and then we have the set of the equivalence classes, sets of n. There's a way of assigning a number to its corresponding class, and this assignment is called the projection operation, pi, right? So this relation between the original set and the set of equivalence classes is called a projection. So what happens is that, first of all, these operations are well defined. Observation plus and multiplication in subset n are well defined. Yeah, we can prove that this is well done. We can do that in a minute. And also, observation 2, the projection is compatible with the ring operations. That is, this definition that we have written here has the following consequence. If we want to project A plus B, what we get is the projection of A plus the projection of B, and also the projection of the multiplication is the multiplication of the projections. That is, pi results in a morphism of rings, right? So we are sending a ring, that's Z, that's the original one, and we're cramming it into a very small place that is also a ring because of these definitions and its well-definedness, basically. So this is a very easy thing to prove, and we can leave this for the viewer. It's a very nice exercise. But what does it mean? It means that whenever I want to add the class of A and the class of B, here I can place any member of the equivalence class of A, and here I can place any member of the equivalence class of B, and the result is the same, right? That is to prove that it's well defined. But in the bigger picture, once we get over that detail, we start with a commutative ring, that's Z, and using an equivalence relation, we find a finite set, which is the set of the equivalence classes, that can be endowed with addition and multiplication, in the way that it becomes also a ring. And the thing is, and this is an important observation, theorem, C sub n is a field if and only if n is a prime number. Right? And this is actually a very interesting thing because equivalence relations in general do not yield fields. The only time when that happens is when the equivalence relation is to look at numbers modulo a prime. So examples, set 2, sub 3, sub 5, all these are finite fields. So, just to be explicit, so a class of 0 and the class of 1 is a field of 2 elements. C sub 3, 0, 1, and 2. This is a field of 3 elements. C sub 5, so we have the class of 0, class of 1, class of 2, class of 3, and class of 4 is a field of 5 elements. In general, for prime P, Z sub P is a field of P elements. We're going to discuss this topic more deeply in our upcoming video, when we're going to devote ourselves to the study of these rings and these fields. And we're going to show some differences between C sub 3 and C sub 4. For instance, we're going to compare a ring and a field, and we're going to show why do we need to have a prime number defining the equivalence relation. So there are finite fields. We can construct them using equivalence relations. We're going to show in the next video how we can visualize finite fields and how we can actually build more complicated fields using finite fields. And also recurring to polynomials, right? So I think we're going to stop for now. We have several directions to go from here. We can take a look at functions. We can take a look at equivalence relations. We can take a look at how finite fields work, and maybe dive a little bit into the abelian group concept, which is going to pop up several times within the same conversation. And this is it for now, I guess. In the next video, we're going to dive a little bit deeper into this, and it's going to be a lot of fun. So I hope you enjoyed this video. You can just take a look at it as many times as you want, and we'll see you in the next one. Okay? Goodbye.